All right. We are not going to cover 10.3 because this is just double integral that you're supposed to know. 10.1 is about line integral. How do we define the line integrals? A line integral vector field F, which has three components. See, it's a vector field. It has three components: F1, F2, F3. Each one is a function of x, y, z. Means at each point in space, you have a vector, or assign a vector to each point in a space. And R is the position vector. The line integral of this F over the curve C from point A to point B is defined by this expression, f of R dot dr, integral over C as f as a function of R dot dr. And what this means is that we break the path into very small pieces dr, moving along the path. At any point along that path, we multiply dr, the dot product, by the field at that point, f. And when we do the dot product, we get a scalar. We add all the scalars along the path, and we get the total value. We can write that, of course, you see f has three components, dr has three components, dx, dy, dz. And the dot product means first component of f times the first component of dr, and so forth, adding together gives you a scalar. If the curve C is parameterized with parameter t, like f of r of t equal to x of t, y of t, z of t, with positive orientation from point A to point B. And of course, t goes from A to B. And when t is equal to little a, we are at point A. When t is equal to little b, we are at point B. And then in terms of the parameter, we can write integral of f dot dr in terms of t. And of course, d of r of t becomes r prime of t dt. We can write it this way. F of r of t means f is a function of r is a function of t. So the whole thing here becomes a function of t. And r prime is a function of t because r is a function of t. And then the dot product becomes a function of t. And then integrate over t from the parameter t from little a to little b, right? So basically, we write everything in terms of t and take the integral of a simple function of t. We can write this one now as this. You see f1, f2, f3 dotted by x prime, y prime, z prime, which are the components of r prime. Okay? So there are different ways of looking at it, but they are all saying the same thing. Any questions so far? All right. One example is work of gravity as a line integral of gravitational force. Let's say we have a mass capital M at the origin and another mass lowercase m at some point in space. And this capital M applies the force on F. Of course, this one applies the force on that one, but that we're not considering that. We're just considering what force applies to this little m. The gravitational force on that little m is a vector function or vector field, f as a function of r, which can be given by this formula, which is the gravitational Newton's law of gravitation. And the magnitude is given by gmm over r squared, but it is in the negative r hat direction. So that r is from here to here. R hat is the vector pointing to m, and toward m. And then negative r hat is opposite, means that this force is in the negative of r hat, which is attractive force. Because it is attractive, there is a negative sign here, right? And then we want to find the work of this force moving from A to B. Let's say point A is here. It has a position vector RA, which is that position vector from the origin to that point, to point B, which is here, and has position vector RB, which is this one. And we are going along the path that is called C. Let's say this is the path. And the integral is given by integral f dot dr from A to B along the path C. And what is dr? This dr is along the path, as we said before. It's a small step along the path. At any point, we multiply that dr dot f, and we get a scalar, we add them up. If you want to do calculate that, it is better to go to polar coordinates, because this vector f is along the r hat. In polar coordinate, we have r hat and theta hat, and dr can be written as the increment in r direction times r hat plus the increment of in the theta direction times theta hat. Is how far you go in the azimuthal or theta direction, theta hat direction, depends on how far you are and also what angle you are at. All right, so this is our dr and this is f, and it is easy to calculate f dot dr now because this r hat and theta hat are perpendicular to each other. R hat is the unit vector in the direction of r, and theta hat is the unit vector perpendicular to r hat at any point in counterclockwise direction. It means that we're going this way because theta is from positive x direction counterclockwise. So if if r hat is this way, theta hat in that point is this way, so perpendicular to r hat. Now f is in r hat direction, so f dot dr becomes, you see, this vector dot by this vector. So r hat dot r hat becomes 1, r hat dot theta hat becomes 0. So this term goes away, and this dot product becomes just negative gmm over r squared dr. And then the integral becomes negative gmm over r squared dr from RA to RB. Why is it from RA to RB? Because we have only integral in the R direction. We don't have anything in the theta direction. So that depends only on how much R changes. So we can put all these negative signs outside, negative signs and constants outside, and the integral from RA to RB, r to the negative 2, which is this 1 over r squared, dr. And integral of negative r to the negative 2 becomes r to the negative 1. So 1 over r from RA to RB means that evaluate this at RB minus evaluation of that in RA. So it becomes gmm 1 over RB minus 1 over RA, right? And then we can write this as negative of U gravitational potential energy at point B minus gravitational potential energy at point A, or negative change of gravitational potential energy, which is this function, negative of gm m over r. There are some negatives here, and it seems arbitrary, but because of technical things, the way we do physics, we need this negative sign to have the conservation of energy at the end. I'm going to talk about that later a little bit maybe. All right, so this is the work of gravity as a line integral of gravitational force that becomes the change of this function. we actually calculated that here, and can be written as change of this function from point A to point B, which is called gravitational potential energy. Any questions on this? All right. Mathematically, you can just do line integral without any physical meaning sometimes on a curve. Like this helix goes from A to B along this path, helical path, that is parameterized with parameter t. And f is given by this. You see, usually r is xyz, but f is zxy. What this means is that the x component of f is the same as the value of z at any point, position z. And the y component is how much x is, and the z component is how much y is. It's a weird function, but it's a mathematical function. It's okay. And r is parameterized. This is parametric representation of this helix. You see that this has x is 3 cosine t, y is 3 sine t, so it means that xy is like on this circle. But as the xy moves along this circle, z changes vertically. So as we go along with this circle, we also move up. So we go along this helical path. And t goes from 0 to 2 pi. You want to calculate the line integral for this. So we say we have f of r of t, means f as a function of r as a function of t. R is a function of t, f is a function of the xyz. So you see, the x component of f is z, but z is t. So we put t here. Y component of r is x, but x is this one. So we put for y component this function of t, and z component is y. Y is 3 sine t. We put that in here. And r prime is the derivative of this r, which is negative 3 sine t, and 3 cosine t, and 1. The derivative of this r with respect to t. So now the integral we say is f dot r prime dt. This is f dot r prime, then integral over t. So if you do f dot r prime, this is f, this is r prime. So it becomes t times negative 3 sine t, negative 3t sine t. Then 3 cosine t times 3 cosine t becomes 9 cosine squared. And then 3 sine t times 1 becomes just 3 sine t dt. So what is this integral? In order to calculate this integral, this is 3 terms. You can separate them and do three integral. Integral of this one plus integral of this one plus integral of this one. By this, you can factor also negative 3 and find the integral of t sine t. So what is integral of t sine t? How do we find integral of t sine t? Do you remember? From techniques of integration, yes?
Product rule?
Product rule. What do you mean by that? It might,
no, that's just for derivatives, right?
Yeah, okay. Product rule, but we use product rule to, yeah, somebody, Krishi says by parts, yes. Integration by parts means that if you have uv, I think what you meant is that if you have udv, you can write it as uv minus integral of vd. So we need to do by part here to get rid of this t here. So we take sine of t dt as dv. So v becomes negative cosine t, and then we take t as u, and dt becomes du. And then the integral of, we have u dv becomes uv minus integral v du. Okay. And so u is this t, v is the negative cosine t. So negative t cosine t evaluated from 0 to 2 pi minus the integral of v du. V is this, du is this. So that's that way we get rid of this t here. All right. So we have that. And what is the cosine? What is the integral of cosine from 0 to 2 pi? Because cosine of t is periodic from 0 to 2 pi becomes 0, right? And this one becomes just negative 2 pi minus 0, so negative 2 pi, right? If you put 2 pi becomes negative 2 pi cosine of 2 pi, which is 1. If you put 0, becomes negative 0 times cosine becomes 0. And then integral of this cosine squared, we can write it in, do you remember? How do you do cosine squared? Integral.
Oh wait, never mind.
You could do a trig identity.
Yeah, trig identity, double angle, right? We do 1/2 of 1 plus cosine of 2t for cosine squared. And then cosine 2t integral becomes 0 in this case. So we have integral of 1/2 and times dt. Integral of dt becomes 2 pi times 1/2 becomes pi. And then what is the integral of sine t dt? Integral of sine is periodic again with the period of 2 pi, so it becomes 0, right? So if you put back this these values into this, we have negative 3t sine t. So the integral becomes negative 3 times the integral of t sine t, which we found as 2 pi. And then 9 integral of cosine squared, which is pi, and plus 0, right? So the total becomes negative 6, no, plus 6, negative 3 times negative 2. This is 6 pi, and 9 pi becomes 15 pi, which is 47.124, right? Any questions? So this,
Yeah, what is that actually showing us then? So 47.124 is what exactly?
that's the integral, that's the line integral of this f, this function, over this curve from
So
A
it's
to
a
B.
length? It's a distance?
No, it's not a distance, no.
Okay.
Basically, the unit of that becomes distance squared. We don't have units here, but if these were in meters, let's say, and this was in meters as well, then it will be meters squared because this is dot product, right?
Right,
Meters
okay.
times meters. But here is just math. It doesn't have dimensions. So it's just a number. That is the line integral of this function, this vector field, when you take along this path from A to B, which is this. So this is that, which becomes that integral, and then becomes 47. Okay. Did I answer your question?
Yeah. So yes, thank you.
Yeah, you're welcome. All right. So this example that shows how to do the integral if you have the curve parameterized with parameter t. Okay. And of course, we have a vector field here. All right. General properties of line integrals are the same as general properties of integrals that you had, because the way they are defined, for every constant c and for every integrable vector fields f and g, and every piecewise smooth curve c that can be divided into two pieces, c1 and c2, with the same positive orientation, we have these properties. If you have integral of cf dot dr, which c is a constant, that constant comes out like what you have in the ordinary integrals. If you have integral of f plus g dot dr, becomes integral of f dot dr plus integral of g dot dr over the same path c. And if you have a curve C from A to B that can be divided into two pieces, C1 and C2, then integral of f dot dr over curve C is the same as integral f dot dr over C1 plus integral f dot dr over C2. Means basically you can break it into two pieces or more, right? In each of the first two, the orientation of C is the same in here. And if this sense of integration along C is reversed, the value of integral is multiplied by a -1. This is the same as, you know, with, in calculus, we say integral from A to B of fx dx equals a negative of integral from B to A. If you switch the limits of the integral, you have a negative sign appearing. This is the same thing. So basically the integral, very intuitive. We can use these properties every time you want. All right. One example that's given in the book, and it's also very important in physics, in mechanics, is that the net work done on an object by all the forces is equal to the change in kinetic energy from point A to point B. So from Newton's law, we have F net equal to ma. A is the derivative of acceleration, is derivative of velocity, right? dv dt, where t is the time parameter. So in physics, this t is time parameter. In mathematics, it doesn't have to be anything meaningful. It's just a parameter. But in physics, that t has a meaning. It's a time. A is the acceleration vector. V is the velocity vector with magnitude. Lowercase v, you see not boldface, it's italic. We mean the speed, the magnitude of velocity. Then we have net work, W net, equal to integral from A to B, point A to point B, F net dot dr, net force dot dr. This is the line integral of the net force, which is the W, which is work. Remember, work is defined like that in physics. And we can write it in terms of parameter t, which is time in this case, becomes F net at any point r as a function of t time dot r prime of t dt. That is the math that we just went over, but F net of r dt at point t becomes the m times the acceleration, because F net is mass times acceleration. This just tells you explicitly that it is a function of the position. So we have ma here because of Newton's law, and this is the rest of it. We just dropped the time dependence because we know these are all time dependent. And now this a is the derivative of velocity, we call it v prime, and r prime is the derivative of position vector, which is the velocity vector. So instead of a, we put v prime, instead of r prime, we put v. And m can come out. This is v prime dot v. We can write it as v dot v prime. Remember, we had if you have a vector, if you have a dot product of two vectors, you can write the derivative of that is derivative of first one times the second one plus derivative of second one times the first one. But in this case, both of them are the same vector. So we can write it as 1/2 v dot v prime. So because this one becomes v prime dot v plus v dot v prime, and both of them are the same, so it becomes twice that, right? Instead of, so this one is half of this. So we have 1/2 m v dot v prime. And what is v dot v? A vector dotted by itself becomes magnitude squared, right? So it becomes 1/2 m that comes out of the integral, and then v squared prime. V squared prime basically is rate of change of v squared with respect to time, then times dt. So this is dv squared over dt times dt. It becomes d of v squared. So the integral becomes just v squared. Or derivative of, or integral of derivative becomes the value, the function itself, right? So we have 1/2 mv squared, and then evaluate that between t equal to a and t equal to b. So that becomes 1/2 mv squared when t is equal to b, which means that when we are at point b, you see at point b, t is equal to b. At point a, t is equal to a. So when you evaluate that at t equal to b, we get the velocity or speed squared at point b, and when you evaluate at point little a, we get velocity or speed squared at point a. So it becomes 1/2 mvb squared minus 1/2 mva squared. And that means kinetic energy at point B minus kinetic energy at point A. So we see that the net work on an object is equal to change of its kinetic energy between point A and point B. This is very important in physics. We call it the work energy theorem. All right. The net work done on an object from point A to point B is equal to the change of its kinetic energy between point A and point B. So this is work energy theorem. Any questions? Yeah, where does the 1/2 come from? From here. Let me explain in more details here. You see, we have if you calculate this, you have v dot v prime. So we said that this is derivative with respect to time. So it becomes v prime dot v plus v dot v prime. But these are the same. Dot product is commutative. So it becomes twice v prime dot v. But here we have one of them. So v dot v, v prime dot v becomes 1/2 v dot v prime. That's where the 1/2 comes from, somebody else. Okay. Any questions? All right. So sometimes we have other forms of line integrals. This is not unique. This is generally the line integral f dot dr, but we can define line integrals another way. And for that, let's say we can define line integral like this. If the original definition of line integral is evaluated without the dot product with dr, but instead the integral is taken over the parameter t, what do we have? We have a vector, because integral f dt is integral f of r of t dt, and that has 3 components: x component, y component, z component. These are not derivatives. I should write f1, f2, f3 as consistent with the book, because we use the subscript xyz when we mean the partial derivative, but here it's not partial derivative. It's the 3 components, and then the integral can be taken over each part, so becomes a vector. Each component of the vector is the integral of f, that component with respect to time. So we get a vector. In physics, if t is time and f of r of t is the net force acting on an object, this line integral represents the net impulse. We call it impulse f. We call it impulse with the notation j. It is the impulse imparted on the object in moving from point A to point B, and is equal to the object's total change of momentum vector. Momentum is mv, and the total change in momentum vector becomes the impulse. So J becomes delta P. And that is mv final minus mv initial, or v at point B minus v at point A. This is called momentum impulse momentum theorem in mechanics. And so if you multiply force by time, you get impulse, and that changes its momentum. It's equals to change in momentum. But if you do dot product of force and direction, I mean dot dr, and integrate, that becomes work, which is equal to change of kinetic energy. Basically, these are also manifestation of Newton's law. This is equivalent to F equals ma. The other one is equivalent of F equals ma again, but there are different ways of looking at the same problem. This is another application of line integrals if they are defined differently. Okay. All right. So now we want to show that this line integral that we found is in fact path dependent. In general, the line integrals depend not only on the vector field and the endpoints, but also depend on the path taken. For example, evaluate the line integral of f. This is the vector field. It is only in y direction, but the magnitude depends on the position x and y. From the origin to the point 2 and 4 along two different paths. So we have this field. We want to take the line integral of that along two different paths. One is the straight line that goes from origin to this point 2.4 directly. You see, if you put t equal to 0, you get the origin, 0 and 0, 0. And if you take any other point, y is equal to 2x. Y equal to 2x is a line. We go along that line, right? This parametric, this is a parametric representation of this line, right? So this is the straight line segment. And then the other path we want to take is the parabola R2 of t, which is t squared, and 0. Here, if this is x and this is y, y is equal to x squared. This is a parabola. So we have these two paths. We want to see what is the line integral of f along each path. All right. On R1 of t, we have f of R1 equal to 2t squared for y component. X component 0. Y component is xy. In R1, x is t and y is 2t. So if you multiply, you get 2t squared. And R1 prime is what? R1 prime is the derivative of this with respect to t, which is 1 and 2. So R1 prime is just a constant vector 1 and 2. And f dot r prime, it becomes this vector dot this vector, which is 0 times 1, 2t squared times 2, and 0 times 0 added together. So 2t squared times 2 becomes 4t squared, right? So we have this. And now we are ready to do the integral of f dot r prime dt. I should put dt here. Is equal to this f dot r prime dt, so 4t squared dt. And that becomes what? Becomes, becomes 4/3 of t cubed evaluated between 0 and 2. If you put t 2 cubed becomes 8 times 4, is 32/3, right? So 32/3, which is 10.67 or 10 2/3, right? Along the other path, parabola, see f of R2, which is 0, xy, this is x, this is y, so xy becomes R cubed, t cubed, and 0. And R prime becomes 0, 1, 2t, and 0. And f dot R prime becomes 0 times 1, t cubed times 2t becomes 2t4. And 0 times 0, so 0. And we have, then now we're ready to do the integral. Integral of f dot R2 prime dt is equal to integral of 2t4, which is that, dt. So this becomes 2t to the 5th divided by 5, right? And evaluated from 0 to 2. So if you put 2 here for t to the 2 to the 5th times 2 is 2 to the 6th, becomes 64/5, right? So 64/5, which is 12.8. And you see these two are different. Means that the line integral over this path, C1 and C2, and these two are not the same, right? This is over C1, this is over C2. They are not the same, right? So in general, the line integrals are path dependent. We want to see now in section 10.2, what are the conditions when the integrals, line integrals, are path independent. So path independence of line integrals. For example, we want to see what conditions should be met in order for the line integral to be the same for any path from A to B, like this C1 and C2. All right, so we're going to talk about that. The line integral of f, which is a vector field, from point A to point B, which is integral from A to B f dot dr, this kind of line integral, in a simply connected domain D is path independent if and only if we have one of the following equivalent conditions. So we have a few conditions, they are equivalent, and they are also equivalent to being path independent. So one of them is f dot dr is an exact differential, which means that f dot dr is d of some function, the total differential. See, is the exact differential of a function f, which is a three-dimensional scalar function. So this is a scalar. This becomes a three-dimensional scalar function. All right. So we say that if this is the case, if f dot dr is the total differential or exact differential of a scalar function, then the line integral is path independent. All right. This means that f dot dr is the total differential of f. But remember, from chain rule in multivariable calculus, in multivariable calculus, the total differential of a function that is the function of some other functions can be written this way. You say the derivative, partial derivative of f with respect to x times differential of x plus partial of the derivative of f with respect to y times derivative of differential of y plus partial derivative of f with respect to z times differential of z. And if you look at that, you see that these three are the components of the gradient of this f. and dx, dy, dz are components of dr. You can write this as gradient of f dot dr. All right, which shows you that saying that f dot dr is exact differential is the same as saying that f can be written as gradient of a scalar function, which is our second condition. If f is a gradient of a scalar function. All right. So these are the same thing, basically. The next condition is when integral of f dot dr over any closed path is 0. When we have closed path, we put a circle on the integral to show that it is a closed path. If we don't put that in here, see, in here we don't have a closed path, it's general. But here it says that integral of f dot dr means line integral of f over any closed path is 0 in the domain we're talking about. Well, what does it have to do with integral being path independent? Do you see how this is related to path independence?
Yes.
Yeah. Okay. I explain. I'm sure if you say yes, you see it now. You see, if you go, if you take a path from A to B and then come back to A, means that along this path that is closed. If integral over C closed path of f dot dr is equal to 0, means that you can break the integral into two pieces, go from A to B along C, and then go back on C1 and go back on C2. So it becomes integral along C1 f dot dr. I don't write f dot dr because it's doing the same thing. Integral along C1 plus integral along negative C2 means going on C2 but in opposite direction equal to 0. That means that integral along C1 minus integral along C2 equal to 0. That means integral from along C1 is equal to integral along C2, right? So you see, if you have integral around any closed path equal to 0, means that no matter how you go from A to B, all the integrals will be the same. So, you can prove that by going along one path, coming back along another path, and because the total is 0, you can say that going one way along any path is the same. All right. So that shows equivalence of these three with path independence. That's the most obvious one. And then another condition is this one: curl of f is 0. Means that if curl of f is 0 for all points in the domain D, then the path line integral is path independent. How is that possible? What does curl have to do with path independence? We are not going to fully understand this until we get to the end of this chapter, which we discuss this formula, which is the Stokes theorem. It says that the integral, the normal component of the curl of f integrated over the surface S is the same as the path line integral over the path that is the boundaries of this S. This C is boundary of S. And if this is S, then this C that goes around is boundary of S. So this is a Stokes theorem. And now you see that if curl of f is 0 everywhere, this side is 0, then this side should be 0, right? And therefore that gives you the that gives you this one, and that gives you the path independence. All right, and now we want to see how 1 and 2 give you path independence. All right, so let's see if you have the f dot dr as the total differential or exact differential of f, then we can see that this is equal to fb minus fa, because the total, adding the changes becomes the total change. Adding all the changes of some function becomes the total change. Right? This is when, of course, when f can be written as the gradient of a scalar function, this line integral becomes just change of that scalar function. That's why they call it potential function. Also in mathematics, is taken from physics. All right, and so this is not only tells you that the integral, line integral, is path independent, it also tells you how you calculate the line integral. If you know this f, you just calculate at b and calculate at a and subtract, like what we do in normal integration. This is similar to fundamental theorem of calculus that says if you have a function capital F whose derivative is the lowercase f function, then integral from a to b of fx dx becomes capital F evaluated at b minus capital F evaluated at a. Here is the same, but you see that the role of capital and lowercase is changed. In this case, the antiderivative is the lowercase. The derivative is the capital F, which is the vector field. All right. So if the vector field is the gradient of a scalar function, then the line integral can be written as difference of or change of the scalar function. So you see the similarity?
Professor,
Yes.
can you explain again the difference between capital F and lowercase f? You were saying.
Yeah, capital F is our vector field, right? Oops. Oops. Capital F is this, the vector field.
Okay.
And the scalar field is that when we have this condition, you say that a gradient of f is f dot dr, is f. Gradient of f is the vector field. This theorem basically says that if f can be written as gradient of f, then integral of f dot dr becomes this lowercase f evaluated at point b minus lowercase evaluated at point a. That is similar to the fundamental theorem of calculus.
Okay.
So now we see that one, the condition one, going back to these four conditions, the condition 1 and 2 are equivalent, and it obviously gives you path independence. Condition 3 is more closely or more intuitively seen as equivalent of path independence. But for the 4, we need to get to the end of this chapter to fully understand why the curve being 0 is equal to is equivalent to path independence. So we have 4 different conditions for path independence. Okay. All right. So let's go back to an example. Example one says that show that line integral f dot dr, which is given by this, means that f basically the vector field f is these has these components, right? So 2x and 4y, 6y, sorry, and negative 4z. This is f. Show that this line integral for this f is path independent in any domain in space, and find its value in the integration from point A to point B. So how can we do that? There are different ways to do that. One is to find the potential function, and especially it is important to find a potential function or a scalar function whose gradient is f. Can you guess a scalar function whose gradient is f? This one is easy to guess. Sometimes it's not easy to guess. So you want a partial with respect to x to be 2x, and partial with respect to y to be 6y, and partial with respect to z to be negative 4z. So you see that this f, if it is x squared plus 3y squared minus 2z squared, it fulfills this condition, right? Now the gradient of f is equal to f, right? So now that we know there's a scalar function whose gradient is this f, then we can say the integral of the dr is equal to f, this lowercase f evaluated at point B minus f evaluated at point A. Means this f, when x is equal to 1, y is equal to 0, and z equal to 2, no, at point 2, at point B. B is 2, negative 3, and 5 minus f of 1, 0, and 2, right? So we can calculate that. At 2 and negative 3 and 5 means x is 2, so 2 squared plus 3 times negative 3 squared plus minus 2 times z squared, which is 5 squared, right? This is f at this point, and the other one is 1 squared plus 3 times 0 squared minus 2 times 2 squared, right? It becomes, this is 4, this is negative 3 squared, becomes 9 times 3 plus 27, minus 2 times 25 minus 50, minus 1 plus 0 minus 8, right? So this is negative 7, and negative becomes positive 7, and this becomes 50 minus 31, negative 19, and plus 7. So it becomes negative 12, right? So by guessing this function, whose gradient is this function that's under the integral, we can find basically what the integral is from A to B, any point to any other point. So this is again the same thing. 2x, 6y, negative 4z, it's gradient of f, so gradient of this function. So f dot dr is an exact differential, and therefore the given line integral is path independent. Also, f is that, and integral of this becomes integral of d of f, f of b minus f of a, which is, no, just plugging in and getting negative 12. All right. Any questions? All right, I guess it is time to take a break. we can take a break for a few minutes. Let's take a break until 2:05. We resume at 2:05. And meanwhile, I'm here if you have any questions. All right. So this is another example. It says evaluate the line integral 3x squared dx 2yz dy y squared dz from a to b by showing it has a potential f, potential function or scalar function f, whose gradient is f. So what is f here? The vector field is 3x squared and 2yz and y squared, right? So what is f, where gradient of f is equal to f? That is, gradient of f is basically a vector whose components are del f del x, del f del y, and del f del z. Can you guess a function whose gradient is this capital F vector field?
X cubed, y squared z, and then y squared z.
Y squared z and y, 2y squared z, you mean?
No, it would just be y squared. When
Y squared z, right? Yes. Yeah,
for both.
that's right. No, it's just you need a scalar. That function is a scalar. F is a scalar. Remember, I think you're thinking about components, or you're talking about the derivatives. So you see that this should be 3x squared. This derivative with respect to y should be 2yz, and derivative with respect to z should be y squared. So that gives you the hint. Sometimes it is easy to guess, but sometimes it's not easy to guess. If it is not easy to guess, you just follow the procedure. You say, okay, the derivative of f with respect to x should be equal to f1, the x component of f, which is 3x squared. Therefore, now we can solve for f. F should be now x cubed plus a constant, right? But the constant as far as x is concerned. But it can be a function of y and z. So we call it a function g of y and z. Okay? But then we say, okay, we also have derivative of f with respect to y should be equal to f2, which is equal to 2yz, right? Therefore, we take derivative with respect to f of what we have. So we get derivative derivative of g with respect to y should be equal to 2yz. And then we find g. So g becomes y squared z plus a constant. A constant as far as y and x are concerned, so becomes a function of z in general, right? And then if G is that, we put back in here. So F should be, let me write here, F of X, Y, Z should have this form, should have X cubed plus Y squared Z plus H of Z, right? And then we say, okay, to find H of Z, we set the derivative of F with respect to Z equal to F3, which is Y squared.
Professor,
Yes.
I'm confused. So I get the idea that when you integrate, you have to add the constant. I'm confused why the first one is like G of Y and Z, and then the second one is just H of Z. Like,
Yeah, good
where are we
question.
getting those from? And then why does G
Yeah.
equals Y squared Z?
But look, we said that if derivative with respect to X is 3x squared, then F becomes X cubed plus a constant as far as X is concerned, right? So that constant is constant with respect to X. So it can be, in general, a
Okay.
function of Y and Z, right? And in the second step, we find the condition on G. We said the derivative with respect to Y of G should be 2YZ. So G becomes Y squared Z plus a constant. Again, a constant for Y and a constant for X, but it can be a function of Z. Make sense?
The first part made sense to me. I'm still confused on why we can call the YZ G and then why it's not a function of Z or X. Since we're taking the derivative or
Yeah,
integral with respect to Y.
we have this. We solve this for G, right? This is the derivative. Derivative of G is 2YZ. So derivative with respect to Y of G is 2YZ. So if it integrates with respect to Y, becomes Y squared Z, and we say that there's a constant. That constant should be constant when we change X and Y. So far, because this was not a function of X, so the G is not a function of X, and this part of G is a function of Y. This part of G should not be a function of Y either. So it's only a function of Z. Is that not clear? Yeah.
No, not really, but I'll probably just have to do some reading.
It said that, say, if you integrate this, we get a constant of integration as long as Y is concerned. So it should be constant in terms of Y, means doesn't depend on Y, but it can still depend on Z. Or do it this way. Think of it this way. If you take partial derivative of this G with respect to Y, what do you get? You get
2YZ.
yeah, so get this, right? So no matter what function of Z we have, we get this. Means that there's a possibility to have a function of Z here.
But if you had a function of X as well, wouldn't the derivative with
Means
respect
this
to
is
Y
function
still?
of Z and X? Is that what you mean?
Oh, are you, wait, yeah, that's what I was.
No,
thought.
because G originally was not a function of X. It's only a function of, here, G is function of Y and Z only. Right? And now between Y and Z, we say that this part is not a function of Y, it's only a function of Z. All right, and then we put back G in this equation, F becomes X cubed plus YZ plus a function of Z. And then we apply the third condition, said a derivative with respect to Z should be F3, which is Y squared. And if we take derivative of this with respect to Z, it becomes 2YZ no, sorry, it becomes Y squared plus H prime of Z. Derivative of this with respect to Z, right? Becomes y squared plus h prime of z. And you see from this equation, y prime cancels, h prime should be 0. And therefore, h of z should be constant. We can call that constant 0. We can take it to be 0 because that doesn't change anything for us. So one of the functions f that we can get is just f becomes x cubed plus y squared z. Of course, you can add a constant because it doesn't change the gradient. Gradient for every derivative that you take, this c goes away. So we can take it just to be 0. So f is this, right? I don't know. Somebody has again asked where does g and h come from? Am I not saying right correctly? I said that when you take the integral of this function, when you take this integral of this function to get f in terms of x, there's a constant of integration. That is constant as far as x is concerned, so it should be a function of y and z.
Okay, so that's our plus c, but it can no longer include an x term in it.
Yeah, this is c, this is plus c, but
Okay.
as far as x is concerned, it can be a function of y and z. Or again, look at it differently. You can say, okay, I'm saying that in general, f is like that. If you take the partial derivative of this f with respect to x, you get that no matter what g is. So we have this freedom to choose a general g for that.
So essentially, we're narrowing down our plus c. It's no longer like a completely unknown plus c. We can get rid of the x component of it, and that's what we're left with.
Yeah, it is not a function of x, but
Right.
in general can be any function of y and z. Again, when you go one step further, you want to find g, you find g to be y squared z plus a constant, but because you do the integral in here, you do the integral with respect to y, becomes that. This is a constant as far as y is concerned.
Okay, and so by the time we get to z and we've got our constant is equal to 0, we basically narrowed things down so we know that
That's
there's
right.
not even a constant there.
That's right. We can
Okay,
say
thank you.
this is not actually this is not a function. This is not a function of z here. We said it becomes constant, then that we can take that constant to be 0. All right. So we have to find the most general form, but of course this constant plus constant is not going to do anything for us because no matter what constant, you can always add a constant to this function f and still the gradient is the same. Because gradient involves derivatives and that constant goes away. All right, so we have f to be in this form, x cubed plus y squared z. And then we want to find the integral from a to b, where a and b are these two. Okay, so we say the integral over curve c becomes this f evaluated at point b minus this f evaluated at point a. So it becomes at point b becomes 2 cubed plus y, which is 3 squared times 0, right? This is at point b minus 1 cubed plus 0 times 0 squared times 1, right? So that's 8 minus 1 becomes 7. Okay. Well, I'll go over it one more time because I have this printed also. So if f is gradient of lowercase f, we should have the partial of f with respect to x equal to f1, which is 3x squared. That gives us f equal to x cubed plus g of y and z. Why is it g of y and z? Because we have a constant of integration for x. It's a constant with respect to x. Or if you take derivative of this with respect to x, you get the same thing, no matter what g is. But so in general, that part is function of y and z. And then fy should be equal to f2, which is 2yz. And let's take the derivative with respect to y of what we had here. See, take derivative with respect to y. This one is not function of y, so it becomes just derivative with respect to y of g equal to 2yz. Then gyz becomes y squared z because of plus constant as long as y is concerned, right? So it can be a function of z. It's not a function of y, it's a constant for y, but it's a constant is the z, function of z. So f becomes like that, and then partial with respect to z should be f3, which is y squared. So y squared plus h, well, see, this is partial with respect to z, becomes y squared plus h prime, which should be equal to y squared. So h prime is 0, so h is equal to c, and it is 0. So f, we have that, and then integral becomes f of f at 2, 3, 0, and minus f at 1, 0, 1. It becomes that minus that equals 7. Okay.
Okay, sorry. So could you explain one more time in the second line why we're able to say f of y equals gy yz?
Oh, because the fy means this is the same as saying that derivative of f with respect to y, right?
Yeah.
Which is derivative of the other side with respect to y. Derivative of x cubed is 0, so it becomes derivative of g with respect to y. That's what this means, right? We said that index y means derivative with respect to y, partial derivative with respect to y, when you have multivariable functions. All right. Is it still not clear?
No, I think I'll just have to do reading.
Yeah, this is I think the notation. You see, this is our f. What is take derivative with respect to y? This side becomes derivative with respect to y. The other side becomes derivative of g with respect to y. But it should be also equal to this according to our condition. That's putting these two together and taking derivative of that function. And then again, we take antiderivative and so forth. I don't know what is exactly the problem here. The derivative of f with respect to y becomes exactly the derivative of g with respect to y, because the rest of it is a function of x. Right? All right. Probably you need to think about it a little bit.
Professor,
Yes.
for the z component, which would be the y squared, right?
Yeah. You see, this is f3. We said that derivative with respect to z should be equal to f3, which is y squared.
If that y squared was, say, like a z squared, would our potential f be the x cubed plus y squared z? Would it be plus 2z? Or plus some,
fz is equal
would
to.
that z
Oh,
go
what?
away?
No, that's, wait a moment. Y squared. So you see, from this is f, right? F is 3x squared plus, or not plus, so 3 components, 3x squared, 3x squared, and 2yz and y squared. This should be equal to partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z, partial z.
So if it had a z in its component, it wouldn't go away, right?
The book writes this as x, fy, and fz. Right? Is that clear?
Yeah.
The different notations. So this is fy should be equal to y squared. So far we have f is equal to this. We know that fz, oh, fz, fx, fy, fz. So this partial of f with respect to z should be y squared, right? Here. On the other hand, we have this f. We take the partial with respect to z. What is the partial with respect to z here? This one doesn't have any z. This becomes y squared. That becomes h prime. So we say y squared plus h prime equal to y squared. That's how
Okay.
h prime becomes 0.
Yeah.
Did I answer your question?
Yeah.
All right. Any other questions? Still unclear? So the whole thing is to find this f, but we realize that this h can be 0. Anyhow, let's move on. Notice that both line integrals in the previous examples have curl equal to 0. See, this was the first one. We said that integral f dot dr is 2x dx, 6y dy, and negative 4z dz. And look at curl of f. F has these ones, f1, f2, and f3. These 3 components. So the curl of f will be ijk, the partial derivatives, and 2x, 6y, and negative 4z. And you see that all the components of these, determinant is 0. So if you put this and that, derivative with respect to y, derivative with respect to z is 0. If you do look at the y component, derivative of this with respect to x, derivative of this with respect to z is 0. Look at the z component, these derivatives are all 0. So that curl of f is 0. And also for this one, you see that for the x component, derivative of y squared with respect to y becomes 2y. Derivative of 2yz with respect to z becomes also 2y. So they cancel each other, it becomes 0. For the y component, you see 0, 0, everything is 0. So in both of these cases, because there was a potential function, the curl should be 0, and it was 0. Okay. All right. This is another more complicated case. Again, we do the same thing. Let's say if curl of f is 0, we should have, well, let me read the problem. Show that the vector field under the integral sign of this has a 0 curl, so that the integral is path independent, sorry. Then find the potential f such that f equals gradient of f, and evaluate the integral from a to b. So in order to show that the integral is path independent, we show that curl of f is 0. If curl of f is 0, we should have f1y equal to f2x. This is This is the third component of the curl. Z equal to 0 gives us that. And the middle one is the y component of the curl. The last one is the x component of the curl. So we have to have these conditions for the curl to be 0 everywhere. Do we have that? We observe that f1y, we look at f1, this is f1, and this is f2, and this is f3, right? f1y means derivative with respect to y becomes 2x z squared. And now f1y should be equal to f2x, means derivative of f2 with respect to x. Is that? There's no x in here, so derivative of f2 with respect to x becomes 2xz squared. So yes, it is equal. And f1z is 4xyz. And look at the f3x. f3x also is 4x1 xyz. So these are the same. And f2z means derivative of the second one with respect to z is 2x squared z plus cosine of yz minus zy sine yz. And you look at the derivative of the third one with respect to y. So it becomes 2x squared z and derivative of y cosine yz in terms of y becomes cosine of yz minus zy sine yz. So this is also the same. So we see that these three conditions are met, means all the components of the curl is 0. So the curl of f is 0, therefore the integral is path independent. And there exists a potential function f such that f is equal to gradient of f. So now we're going to find this f the same way. Find potential f. So what do? We put the derivative with respect to x of f equal to f1, which is 2xyz squared. It's the same process. If you have any questions left, pay attention here. So x derivative with respect to x, partial of f with respect to x is f1, which is 2xyz. This is f1, right? And then, so we integrate this with respect to x. We get x squared yz squared plus a constant. Constant as far as x is concerned. So it could be a function of y and z. So we call it g of yz, right? And then we say that this derivative of this now with respect to y should be equal to f2. Fy should be equal to f2. So derivative of this with respect to y becomes x squared z squared plus partial derivative of g with respect to y. That should be equal to this second part of this, x squared z squared plus z cosine of yz. So then gy should be z cosine yz. Then we integrate that with respect to y. And when we integrate, we get sine of yz plus a constant. So the integral of this with respect to y becomes sine of yz divided by z, right? Then z cancels out. And then becomes sine yz plus a constant. The constant is constant as long as y is concerned. So it can be a function of z. Or if you don't understand that, take derivative with respect to g of y. If g is this, any function of h here, we get the same thing, right? We get z cosine of yz, no matter what h of z is. So it's most general case of g. And then if you put g back into f, so you have f is equal to x squared yz, see, plus g. G is sine of yz plus h. You put back in there, we get this for f. And then we have f of derivative of f with respect to z equal to f3. So derivative with respect to f becomes derivative of f with respect to z becomes 2x squared yz plus y cosine of yz plus h prime of z. That should be equal to this. But you see, this has that cancels, this with this cancels. So what we get is h prime of z is equal to 0. Therefore, h is equal to constant, which we can take it to be 0. So f becomes that. All right. And then integral of f dot dr from a to b becomes f of b minus f of a. So this is f of b means put in f, put all coordinates of b, 2, pi, and 3. So it becomes 2 squared pi 3 squared plus sine of yz, which is 3 pi. Sine of 3 pi happens to be 0. This minus 1 squared times 2 times pi over 4 squared. So pi squared over 16 plus sine of 2 times pi over 4 becomes pi over 2. So this becomes 36 pi minus pi squared over 8 minus 1 becomes 110.8. All right. Any questions? All right. So work of gravity as a line integral is again, we talked about that. Negative change in potential energy, gravitational potential energy, but gravitational potential energy is negative gm over r, or we can say v minus va when v is this function. Gradient of v, if v is this function, gradient of v becomes that, which is this is the gradient, has 3 components, 3 operator. Operates on this function. This instead of r, we can put x squared plus y squared plus z squared to the power 1/2. What is the gradient? So let me write here partial with respect to x and partial with respect to y and partial with it has 3 components. Let's calculate the first component. Partial with respect to x of GMM, let me put that in square bracket, and instead of 1 over this parentheses to the power negative and then 1/2, I put it up and make it negative. So x squared plus y squared plus z squared to the power negative 1/2, right? So this becomes GMM. These are coming out of the derivative. And then you have negative 1/2 times the parentheses x squared plus y squared plus z squared to the power negative 3/2 times the derivative of the parentheses with respect to x, which is times 2x, right? Derivative with respect to y of the same thing, you get the same thing. Instead of 2x, you get 2y. And the same for the third one. So if you can factor all these GMM1 and then x squared plus y squared plus z squared to the power negative 3/2, and it becomes like this. GMM over x squared plus y squared plus z squared to the power 3/2. It was in the numerator negative 3/2. We brought it to the denominator. And then the x component has negative 1/2 times 2x, negative 1/2 times 2y, negative 1/2 times 2z. Those 2's cancel. We can also bring the negative sign out. So it becomes negative G M over R cubed times R. And that is exactly f of R that we had originally. All right. So we also showed that curl of f is 0. Curl of this function is 0. I showed that in last chapter. So this shows that irrotationality means curl being 0, path independence, and also having potential function all happen at the same time. Right? This in fact shows that this is the potential function. The gradient of this potential function is just this function f. And also curl is 0. And we know that this path independent, we show that. These are all happening at the same time. That's just a good example. Any questions? All right. As I mentioned, 10.4, 10.3 is omitted because it is just integration, double integral over regions. That's taught in calculus. Now we do Green's theorem in the plane. The assumption is that R is a closed bounded region in the XY plane whose boundary C consists of finitely many smooth curves. Assume that F1 of function of XY and F2 function of XY are functions that are continuous and have continuous partial derivatives. F1 with respect to Y, derivative of F2 with respect to X. So these derivatives are continuous everywhere in some domain containing R. Then we have this formula as the Green's theorem. So what this says is that if you calculate the double integral of this quantity over the region, that is the same as calculating the line integral of this quantity over the boundary of this region. So this C that is here is the boundary of this R. Okay? We integrate along the entire boundary C of R in counterclockwise directions so that R is on the left as we advance in the direction of integration. What does that mean? Is that when you have this region like this, we make a cut here. This is it's not a simply connected region, it's doubly connected region. And what this means is that when you go over the curve here, you go in a way that the region is always to your left. Right? It's always to your left going this way. And you can make a cut here, go here, and go this way. So the region is still on your left. And come back and come here and then continue here. So that's what it is saying. It's counterclockwise. Counterclockwise means that, of course, outside is counterclockwise. Inside it looks clockwise, but it's still it's considered counterclockwise because the region is to the left of you. All right. This theorem can be viewed as this. You see that if you look at this quantity, can you realize that this is a third component, Z component of the curl of F, that you can write as curl of F dot K. So that's the curl of F dot K. On the other side, you have the line integral over the region, over the boundary of R. So this is the vector form. And this is also a special case of the more general Stokes theorem, as I mentioned. The Stokes theorem says that if you calculate the surface integral over any surface of a curl of function f, dot n is the normal unit normal to this curve, to the not curve, surface, then you have the integral here is the normal component of curl of f over the surface. Here you have the line integral of f over the boundary of that surface. If the surface is in the xy direction, in xy plane, then it becomes like that, and then becomes like that. So basically, the Green's theorem is the Stokes theorem when the surface is in the xy plane. Okay, but we are going to talk about this in general later on in this chapter. All right, any questions? All right, let's look at some of the applications of this Green's theorem. We can find the area of a plane region as a line integral over the boundary. For example, if you have that in Green's theorem, you can take f1 to be 0 and f2 to be x. Then you can write, you see, if f1 is 0, this derivative is 0, and derivative of f2 with respect to x is just 1. So the integral on the left side becomes just double integral over the region R of dx dy. This is double integral dA over the region R becomes the area of the region R. On the other hand, if you take f1 to be negative y and f2 to be 0, then again you get the area on the one side, on the other side becomes negative integral of y dx over the boundary. So if you have the area equal to that, area equal to that, then if you add the two equations, you get twice the area equal to sum of the other two, and then we get area equal to half of the sum of the two. So we can write the area of a region as 1/2 the integral over the boundary of the region of x dy minus y dx. All right. So this can be viewed as a formula. Now we can apply it to different situations. So for example, for an ellipse, x squared over a squared plus y squared over b squared equal to 1, you have parametric representation of this ellipse, a cosine t, b sine t, and then you calculate the derivative of r, and then we can write this in terms of time and in terms of t parameter. We can write as x dy minus y dx becomes x y prime minus y x prime dt, and you can calculate the area to be like that. So if you do x y prime, this is x, this is y prime, this is y, this is x prime. If you do that, you say you get that. AB can be factored, comes out, cosine squared plus sine squared is 1. So you get the 2 pi times 1/2 AB, so it becomes pi AB. That is the area of the ellipse, as you know from before. Another case, the area of a plane region in polar coordinates. We have x equal to r cosine theta, y equal to r sine theta for the polar coordinate. And then dx can be written like that, dy can be written like that. This is because we have multivariable calculus. We have dx differential becomes partial of x with respect to r times dr, and plus partial of x with respect to theta times d theta. This is general differential from chain rule in multivariable calculus, and then you see that dx becomes that because partial x with respect to r becomes cosine. That's cosine theta dr. minus partial plus partial with respect to theta. Partial with respect to theta of x becomes negative sine theta, negative r sine theta d theta. So you see, that's the same with this one. Then you can calculate x dy, y dx. Just multiply all of these together, you get, it simplifies to r squared d theta, and then the area becomes like this, 1/2 integral of r squared d theta. Another way you can look at that, let me go to the example. For example, for the cardioid, r equal to a times 1 minus cosine theta, where theta is from 0 to 2 pi. See, when theta is 0, you are r is also 0. But then as theta increases, this becomes more larger. You see, becomes like that. Becomes like something like this. That's why it's like a heart shape. And when theta is 90 degrees, cosine theta is 0. So it is, this distance becomes a. And this is also a, this distance becomes 2a. So we want to find the area of this cardioid. And the area becomes 1/2 integral r squared d theta. If you take, you see, this is at any point, this is r, and this is d theta is like cut like this. This the difference is d theta. It's hard to draw nicely. So this is d theta. So if you want to calculate, it's kind of like calculating this triangle. This is base times the height divided by 2. The height of it is r. The base of it is r d theta. So it becomes 1/2 base, which is r d theta, times the height, which is r. So it becomes 1/2 r squared d theta. And you see that the area becomes 1/2 r squared d theta. And 1/2 can come out because all of them have 1/2. So 1/2, in this case, r is this, a squared times 1 minus cosine theta squared. And if you square that, it becomes 1 plus cosine squared minus 2 cosine theta. And remember, the integral of 1 becomes 2 pi, integral of cosine squared becomes pi, integral of cosine becomes 0. So it becomes 1/2 a squared times 2 pi plus pi becomes 3/2 pi a squared. Right? So that's the area of a cardioid. You do that, probably you have this in your calculus, but here comes from these as well. This is the homework for these 3 sections. 4, 5, 12b for section 1, 4, 5, 6 for section 2, and 4, 2, 3, 5, section 4. Any questions?
The due dates on it, Professor?
Due date is usually next week.
Next week, along with the previous homework?
Yeah, I didn't put the previous homework on.
No, you did not.
Wow, I forgot. Sorry about that. I will put that up to right now.
Yeah, Professor.
Yes.
Also, the quiz isn't posted as well.
Yeah, today I didn't have a quiz for you. Next time.
Oh, okay.
Yeah, because the syllabus said it's today.
Oh, don't worry about it. Syllabus is tentative.
Okay.
Yeah.
Thank you, Professor.
Yeah, I will give you a quiz next time.
So both homeworks are due next week.
That homework I didn't put up. Do you have it ready or not?
No, I don't. I was hoping it would be ready for next
Oh.
week.
All right, I'll give you until next week because I forgot to put it up.
All good. Thank you.
Mhm.
Thank you, Professor.
You're
Thank you,
welcome.
Professor.
Have a good day and have a good weekend. If you have any questions, I'll be here for a while. Not, see you next week.
Have a good weekend. Bye-bye.
Bye.